Okay, so this section is on analyzing the graph of a function and kind of different parts of that. So the first thing that we will look at is the symmetry of a function. So first off is even symmetry. So a function has even symmetry if and only if it has both points xy and the point negative xy. Basically saying if you can plug in a negative x and the positive x of a function, you get the same thing, okay? So let's kind of think about that a little bit more, right? Let's think about what that could look like. So what if we have x squared, right? So if we look at this, if we plug in x and that same negative x, we get the same y value, right? Because if we look at it, right, we see this line kind of is right across from the same y's, the same y from the different x's. So let's kind of think of one just to see how it works with the actual function, not just looking at the graph. Let's say we're plugging in 3. So if we do if f of 3, right, we want to find what that equals. Well, 3 squared is 9. So to check this, we want to see if we can plug in negative 3 to get the same value. Well, okay, negative 3 squared, make sure that you're squaring the negative and putting parentheses on it then, is equal to, well, also positive 9. Because we got the same value from the positive and the negative of the same number, well, that means this function is even. Another kind of little clue thing to look for is that it has an even exponent value on every term. Now, this is a little bit hard to think about sometimes because there's different functions that are not exponents, right? And then are they even, are they not? So you do have to actually write it out like this to truly see if it's an even function or not. So another thing that we call this is it's reflected about the y-axis, because if we look at this here, right, everything along the y-axis is mirrored this way and this way, right? So it's the same on both sides of the y-axis. Okay, so then the next type of symmetry we want to look at, another example of even symmetry would be this function. It's mirrored exactly again across the y-axis. So both of these are even symmetry. What about this last one? Is this one mirrored across the y-axis? Well, if we kind of think about our line here, oops, that is not the right place. Okay, if we think about our line here, right, along the y-axis, well, there's a hump here and not a hump here, right? So this would not have even symmetry, okay? This is not symmetrical or reflected about the y-axis. So it's pretty easy to see on this one if it's even symmetrical or not if you're looking at the graph. Okay, so now let's look at this one. If we look at these two, right, we can kind of see what's happening again. This is a little bit different though. Odd with plugging in the negative x value. Pen won't work, there we go. If we plug in that negative x value, it doesn't go away and give us the same y, it gives us a negative y, okay? So if we look at these two graphs, well, plug in x, get f of x, plug in negative x, get negative f of x, right? So that seemingly kind of works on this one and on this one over here, right? Another kind of cool thing to think about this is kind of symmetrical about the origin. Now remember, the origin is this point right here connecting the two axes. So if we think about this, what does that mean? Well, it's symmetrical about the origin. That means it rotates to be symmetrical, okay? Rotating symmetry. If you look at it right side up and upside down, it should look the same. So let's check on this graph right here, on the left one. If we flip it upside down, it looks exactly the same, right? So this graph is symmetrical around the origin, or has odd symmetry. Now there's a third version of symmetry that we don't talk about as much. It's x-axis symmetry. It doesn't even have a nice name like even and odd, okay? It's literally just how before we had the kind of reflecting about the y-axis, now x-axis symmetry just reflects about the x-axis, right? So it would be maybe a graph like this, right? So it's not even a function now anymore, okay? So it's a little bit harder to think about in those terms. All right, so then let's see. Let's do an example here. If we look at that first one, is it even symmetry? Does it reflect about the y-axis, right? So if we think about drawing our line down here, well, there's something and there's the same thing, right? It follows the same pattern on both sides of the y-axis, so this would be even symmetry. Let's look at the next graph. So, is it reflected about the y-axis? No, right? It's up on this side and then down on the other. So that means it's not even. We can kind of cross that one off. Is it odd? If we look at it upside down, does it look the same, right? So kind of an easy way to check for that is literally I even look at the computer screen upside down myself. So it's a little easier probably for you guys at home with laptops or tablets or different things, right? So literally just turn it upside down. Okay, it's now going up to the left and down to the right. If we look at it right side up to the left, down to the right. That's the same thing, right? So this one is odd symmetry, or reflected or rotated around the origin. Okay, so now let's look at that first function, g of x. Is that one even or odd? Well, there's, again, something we can look for. Those exponents are odd. So that makes it think that it's probably odd symmetry. Now let's remember, what does it mean to be odd symmetry? Well, odd symmetry is plugging in a negative x and getting out a negative y. Okay, so if we plug in, let's pick something easy, right? 1 and negative 1. Or, well, technically, right, numbers can fool us sometimes. It could be a specific point that works, right? So actually we don't want to use an example with a number, okay? We actually want to plug in x and negative x. Well, we already know what g of x is. It's negative 2x to the 5th plus 7x cubed. We want to now plug in g of negative x. Well, that means we have negative 2 negative x to the 5th plus 7 negative x to the 3rd. Okay, so negatives to odd exponents, they come out, right? Because you can multiply something negative 5 times or 3 times together and it's still negative. So that means this is equal to negative 2 times negative, right? The negative 1 just comes out of the exponent. So that turns into a positive 2. Then, well, we don't need the parenthesis anymore. So then just x to the 5th. Now, again, the same thing happens on the 3. So positive 7, negative, so negative 7x cubed. Okay, now what we want to look for is if we can factor out a negative, does it look the same as what we started with g of x? So negative, then we would have had, well, negative 2x to the 5th plus 7x cubed. That's exactly what we started with here in the parentheses. Just with that negative outside, this means that this is g of negative x equals negative g of x. This is proof that this is odd symmetry. So those exponents being odd do make it odd. But again, I would always check just to be sure. Okay, so g of x is odd. Now let's think about h of x. H of x is, again, we need to look at the exponents. So what do we have? We have an odd exponent and an even exponent. Well, so we don't know what to do with that. Is it even? Is it odd? Is it neither? Let's check again. Every time you check, you're plugging in negative x to see what it does to the original function. Does the negative go away? Does the negative come out and be factorable and make it just negative of the original function, right? Those are the two different options. If it doesn't do either of those, well, then it's neither. Okay, so we want to find h of negative x. Well, we have negative 2 times negative x to the 5th plus 5 negative x to the 2nd. Okay, again, we know what negative x to the 5th does. It just brings that negative out. So that is positive 2x to the 5th. And then negative x squared. Well, squaring something negative makes the negative go away, right? So this stays as plus 5x squared. That means, okay, what happened? If we look at it, it's not the same as what it originally started as. So that means it's not even symmetry, because remember, even symmetry is f of x equals f of negative x. Okay, so it's not even. We can kind of cross that option off. Okay, is it odd? Did it completely change, right? So let's try factoring out a negative. If we pull a negative out of both, that makes it negative 2x to the 5th minus 5x squared. So are the inside of the parentheses what we started with originally? No, because we started out with positive 5x squared, not negative 5x squared. That means it's not odd either, because odd is f of negative x equals negative f of x, right? So that means it's neither, because it didn't completely go away, the negative, or it didn't completely come out. It kind of did a little bit of both. So that means you can't mix them, and you have neither symmetry. Okay? All right, so now the next thing we want to talk about with functions and graphs is about intervals where a function is positive or negative. Okay, so what you want to start with is find where the zeros of the function happen, and then select sections that are all positive and all negative. Now that's kind of geared a little bit towards a graph, but you can do this with a function by setting it equal to 0. That's how you find the zeros of a function, right? And then you can just plug in points around those zeros to see, okay, am I getting positive? Am I getting negative? And then sometimes you might be setting that up in interval notation, or just kind of picking if a point is positive or negative. We'll do some examples after this. So then the next thing we want to talk about is intervals in which a function is increasing or decreasing. Okay, so what does it mean to be increasing or decreasing? One thing we want to make sure to remember is that when we talk about increasing and decreasing or positive, negative, or anything about a graph, when we look at a graph, we read a graph just like we read English, from left to right, okay? So make sure to always look and follow the graph. Don't like pick a point and then look to both sides, because if we look at a point and we have, right, a graph like this, and we look here, it's not increasing on both sides. It's not going up on both sides. We would follow the graph like that, okay, from the left to right direction. All right, so now let's talk about the formal definition of increasing. A function is increasing on the interval, that's the I, on the I interval, if for all x1 and x2, so all x values, f of x2 is greater than f of x1. Okay, so let's break that down. What does that mean? because that formal definition doesn't mean much to us, right? So what we're saying is if we have kind of a graph here, right? We have an x1 and an x2. So if we plug those points in, we get y values, f of x2, f of x1. Then f of x2 needs to be bigger than f of x1. Okay, so the y point needs to be bigger than the y point for x1. So as we get bigger x, we get bigger y. That makes sense, right? So as we increase, we have to increase along the y as well. That's increasing. Makes sense. Okay, let's think about decreasing now. Function is decreasing on the interval if for all x1 and x2, f of x2 is less than f of x1. Okay, again, let's think about a graph of this. So we have, again, x1 and x2. So we're saying here that f of x2, the y value, needs to be smaller than f of x1. So we should be down here and up here. So as we increase on x, we decrease on y. Remember, we're increasing on x because we always look from left to right, okay? So that means from left to right, we go down in y. Just like increasing, we go left to right, we go up on y, okay? So there's kind of a hidden third thing we need to think about. When a function is not increasing or decreasing, we call it constant, okay? It's not changing, it's consistent. Function is constant on the interval I if for all x1 and x2, the function equals, right? It has the same y values. So again, let's think about the graph. We have our graph, right? We have our x1. Oops, I just did it underneath where the video is going to show up. Okay, I'll draw my graph over here. We have x1 and x2. So if we have here a point here, we have a point here, and it does not change. Okay? So then we have increasing, decreasing, constant, and then remember, we also still have the positive and negative points to think about. So what do those kind of things mean, right? Positive and negative, well, that's just where the point is. Is it above the x-axis? Is it below the x-axis? Technically, it could be on the x-axis, and it would be a 0. Now, increasing, decreasing is what is the point or the function doing, right? Is it going down? Is it going up? Is it staying the same? So it's different aspects of a graph or a function that you need to pay attention to for each of those. Okay, so let's look at an example now. If we are asked this type of problem, this is taken directly out of Alex. They're just saying, okay, what is happening at each point? Okay, what's the behavior of the function? So if we look at this, we're asked about point A and B first. So what that means is from A to B, not just A and B. What's happening on this section of the graph right here? Is it going up? Is it going down? Is it staying constant? Increasing, decreasing, constant, right? So we see it's going down from left to right. That section goes down. So A and B is decreasing. Okay, so now we have B and C. Between B and C, we see the function is not going up, not going down. It's staying constant. It's constant section of the graph. Okay, so then C to D. Between C and D, the function is going down, right? So that means, again, it is a decreasing section. Okay, now D and E. Between D and E, the function is going up. So that means it's increasing section. Okay, that's not too bad, right? Looking at a graph and just figuring out, okay, this section is this section is that, not too bad, especially when they give us points that you're just looking between those specific sections of the graph. All right, so the next one, we want to actually put this one in interval notation ourselves. So it's not identified as specific points, A, B, C, D, E, right, as the last one was. We want to put it in interval notation. So let's remember interval notation. Interval notation is the kind of parentheses, like, let's just do a basic one, negative infinity to infinity, or 1 to 3, including 1 and 3, right? So parentheses mean not included, right? And we never include infinity because we can't ever get there. Brackets on the 1 and 3 mean 1 and 3 are included in that section, right? So thinking number line type things, parentheses mean open circles, brackets mean closed circles. Okay, so if we look at this here, we want to follow along and talk about increasing, decreasing, and constant sections. So let's put them in groups. Let's say our increasing pieces are going to be here. Okay, let's just put commas in between the groups that we find. Where's our first increasing piece? Well, the only actually increasing piece, right, is this section right here. So what are the what are the x values? We only care about the x values when we write out interval notation. We do not write this point to this point in ordered pair form. We just say this x to this x value because we're only talking about this function, so we don't need to be more specific than that. Okay, so if we look at the graph here, we have the x values starting at -4, right? So that means we have -4 to, well, -2, right? So what do they get? Do they get parentheses, brackets, what, right? Okay, let's think about this. Do we include those points? Do we not include those points? Let's go back and think about what it said on that kind of description. What it's saying here is that the point after a point needs to be above it or below it to be increasing or decreasing, right? So if we go back and look at our problem that we're talking about here, what we see is that -4 is where it starts increasing, right? The point before it was not an increasing point. So that means we cannot include -4. We put a parenthesis on it. It starts at -4. Then -2, because the point after -2 is not above it, right? That means it's also not an increasing point by definition. So we need to stop there, so put a parenthesis again. Whenever we're putting sections of a graph, talking about increasing, decreasing, and constant sections in interval notation, we're always going to use parentheses, okay? Because we never include those endpoints. All right, so now that we've done the only increasing section, let's do the decreasing sections. Okay, so then decreasing section. If we look here, the very first point at -5x is decreasing, right? So that means we start at -5. Where do we stop? Well, we stop at -4 because that's where the increasing section starts, right? Okay, do we have any more decreasing sections? Well, yes, we do. At +1 to +3. Okay, so let's just kind of list that one as well. In Alex, you could just put a comma in between. That would be fine. So those start at 1 and go to 3. Okay, are there any more decreasing sections? All right, well, we have this section, right? And we have this section. That's it. Okay, so we've done increasing and decreasing. Now let's write out the constant sections. Well, it starts being constant where? Let's look. So at -2. So we say it starts being constant at -2 and stops at +1. Okay. Is there another section? Yeah, the end section, right? Starting at +3 and going to +7. Okay, so now one thing to kind of check is, did we do the whole graph? Did we go all the way from -5 to 7? Okay, well, let's think here. We start at -5, then we go to -4, then we do -4 to -2. We have -2 to 1, 1 to 3, and 3 to 7. So yeah, we went all the way from -5 to 7. So we have marked down and described all of the pieces of this function's graph. Okay, so let's move on to the next idea of discussing graphs. Maximum and minimum values. Okay, so maximum and minimums, they're kind of obvious in thinking, okay, it's the top or the bottom. However, we can have different types of them, okay? We can have global maximums and minimums. We can have local or relative maximums, minimums. We can have endpoint max and mins, okay? So let's think about what each of those things mean. So global means kind of overall, right? The overall top or the overall bottom, right? So global is everywhere. Okay, so everywhere it's a top or everywhere it's a bottom, or max or min, right? So local or relative, they are literally interchangeable. So if we think about that, that literally means on a section of a graph. So a section of a graph has a little top or a little bottom kind of thing. So that would be something like this. This section of the graph has a minimum, right? At this point right here. Or this section of the graph has a top maximum right there. So it's on a section. Okay. So then endpoints, well, that's one's kind of obvious. Endpoint max min, that just means if it has an endpoint. If it starts or stops, right, then those could be maximums or minimums, depending. Okay, we'll look at an example that has that. So the first example is this one. Let's describe each of these points. So let's pick this one right here. This point right here is what? Well, we have global, local, or endpoint. It's not an endpoint, so we can cross that one off right away. It's not a global anything because it's not the overall top or overall bottom, because it goes higher over here, right, and lower over here. So that means it's not a global. Is it a local something? Yeah. Because on this section of the graph, right, it is the bottom. So let's call that point A. Point A is a local minimum. Okay, I kind of use abbreviations there. All right, so now let's think about it. The next point. So the next point we'll think about is this one here. We'll call this one, we said A. So again, let's go through the ideas. It's not an endpoint, it's not a global, right? So it must be a local something, okay? Local maximum, right? Because that little area, so we'll call this one B. B in that area is a local maximum. I use local or relative, just the letter that they are. Little m for minimum, big M for maximum. Or you can fully write it out. I'm good either way. Alex, you will just choose the option most of the times. You won't need to type it out or anything like that. Okay, so then let's move on to the next point, this point here. Okay, let's call it point C. Point C, again, is a local, right? It's a local minimum. And then point D here is a local maximum. Okay, so that one wasn't too bad, right? Let's look at another example. So let's do graph G first. Graph G, well, it has two endpoints. However, notice something really quick here. This endpoint is not a filled in circle, so we actually won't think about that one and consider it an endpoint, okay? However, let's see. What are they asking for? They're asking for the absolute maximum of G and the absolute minimum of G. Okay, so what would they be, right? Okay, absolute maximum. Let's think that one first. Okay. Well, what point is the overall, right? Absolute's another word for global. All right, looking at this graph, the overall top would be right here, right? It's the top point of that graph. So the point that you would put there is, well, let's think it would be xy, right, in ordered pair. It would be negative 4x and what is that? 5y. Okay, so then absolute minimum of G. Well, even though we don't have that point filled in, right? So that's what we have to be careful of. What we would say there, because it's an empty circle, and with empty circles, you never get there, but you're always approaching it closer and closer and closer and closer. We can't actually identify a point that, well, where it stops going down, because it's always getting closer and closer to that three negative 5 point, right? So that means that there is not an absolute minimum for graph G. Okay, that will be an option sometimes. So then let's move on and look at graph H. Graph H, we're still looking for absolutes. So, absolute maximum, does it have one? Well, does it have an overall top, right? That's what we're looking for. One thing that we should notice is that this end over here is an arrow, meaning it's always going up there. It's forever and ever getting closer and closer to that asymptote line, but going up. So that means there's no global maximum or absolute maximum. So again, we would just say none there. Okay, what about absolute minimum? Well, absolute minimum, that's the overall or global minimum. Well, we have kind of two minimum points here. We have this one and this one. However, only one of them is the lowest, right? This one here is at -4. This one is at -5. That means that one wins, the -5 or the end point, okay? So that means the point that we would write is -5, -5. Okay, so let's kind of talk about these points a little bit more, right? These graphs, graph G and H, had local maximums and minimums, right? So a local min here and a local max here. This point right here on graph H is a local max, and then this point here is a local min. So we can have lots of different things within one graph, okay? And then technically we also had some endpoint maximums and minimums, right? Graph G had an endpoint maximum at right here, the absolute max, and graph H had an absolute minimum at the absolute minimum. Sorry, did I say endpoint or absolute? Well, they're both, right? So there's kind of multiple ways always to talk about those different graphs with those points. Okay, so generally though, we will use local or relative, and then we'll talk about absolutes. Those are the ones that we use the most. Okay, so the next thing we talk about is the rate of change and the difference quotient. Okay, so a rate of change is really, it's just slope, right? It's another word for slope. It's generally what we use sometimes in word problems. We talk about rates of change there, or going further into like calculus, we use rate of change when we talk about calculus as well. Okay, so that's the formula. It's delta y over delta x. We talked about that before in section 2.3, that delta just means change. So the change in y over the change in x. If we notice, this is just the function notation version of slope formula, with just the caveat saying that x1 does not equal x2. Okay, there's not 0 in the denominator. We always have that, right? Otherwise, it's not something we can calculate. Okay, so from that, we have the next thing. We have the difference quotient. It's similar. If we notice, we just put a specific kind of combination of points there into the rate of change formula. So what we did was we said instead of x1 and x2, right, we said we had specific points. We said we had x and then f of x, and then we had x plus h and f of x plus h. Because if we put those 2 points in the in the rate of change or the slope formula, we will get the difference quotient. Let's look at that. So f of x plus h minus f of x is the difference in the y's. Then we have x plus h minus x. Well, x plus h minus x is h. That's exactly what we have here in our difference quotient formula, just such that h does not equal 0. Again, meaning these 2 points are not the same point. Okay, that's kind of obvious again because, well, what's the rate of change between the same point? 0. We can't do it. It's not something we talk about. It doesn't make sense, right? So let's do an example for both of these formulas. First one will be the rate of change formula. So with this formula, remember it's just calculating the slope, essentially, except with rates of change, we can talk about rates of change on nonlinear functions. Like this one is a quadratic, right? So what that means is we want to find the y values for both of those x values. So we want to find h of 4 and h of 7. So h of 4, let's plug that in. We get negative 2 times 4 squared minus 3 times 4. So that is 4 squared is 16 times negative 2 is negative 32. Then minus 3 times 4 is minus 12. So h of 4 is equal to negative 44. Okay, so let's then plug in 7. So we have negative 2 times 7 squared minus 3 times 7 is equal to, well, 7 squared is 49 times negative 2 is negative 98. And then negative 3 times 7 is negative 21. Okay, what is that then? That's negative 119. Does that look right? Let's see. Yes. Okay. So we have our 2 points now. Okay, let's check this out. So remember, we want to think about it as rates of change. So that would be h of 7 minus h of 4 over 7 minus 4. Okay, so that would be negative 119 minus negative, so plus 44 over 7 minus 4. Okay, well, what is that simplified down to, right? So we have negative 119 plus 44. Well, that is equal to negative 75 over 7 minus 4 is 3. Well, that simplifies down one more time, right? So negative 75 divided by 3 is negative 25. Okay, so that means the rate of change from x equals 4 to x equals 7 is negative 25. All right, so essentially what we're saying is per every x value, for every one that it moves down, or well, actually up in this case, right, because we're talking about the x still, it's going down 25 between 4 and 7, okay? So this does not say that the whole graph has that same rate of change. That is absolutely not true, right? Because it's a quadratic. Quadratics are not lines, and they're not consistent rates of change or consistent slopes, okay? So just from 4 to 7 has the rate of change of negative 25 on only h of x. All right, so now let's think about an example of the difference quotient. So remember, the difference quotient was f of x plus h minus f of x divided by h. So that means we need to find f of x plus h first. So f of x plus h is function notation, right? For just plugging in, replacing the x's with x plus h. So that means we have x plus h squared minus 4 times x plus h. F of x plus h does not mean x squared minus 4x plus h. We do not just add h on the end. We plug in the quantity x plus h, right? We know that f of 9 would just be 9 squared minus 4 times 9. We do the same thing. We're plugging in something for x. Just because it still has an x in it does not change how we treat it, okay? So let's simplify out this quantity. So we have a FOIL here. That means we get x squared plus xh plus xh plus h squared. And then we can combine like terms, but also multiply the negative 4 through, so minus 4x minus 4h. So that means we simplify combine like terms like we said. So we have x squared plus 2xh plus h squared minus 4x minus 4h. That's just f of x plus h. Now we have to put it into the actual difference quotient here, right? So that means we have x squared plus 2xh plus h squared minus 4x minus 4h minus the quantity x squared minus 4x. That's f of x, remember, over h. So let's think about this formula a little bit, right? We have f of x plus h. That's all of this right there, right? Then we had f of x. That is this function right there. We said f of x plus h minus f of x, all divided by h. So then let's look at what cancels out. We have a minus right here that we distribute. So this minus cancels out the x squareds, and it also cancels out the negative 4x's. So what do we have left? Okay, so we have 2xh plus h squared minus 4h. All of this is gone, so then it's all divided by h. We can simplify one last time. Remember, when we divide an entire kind of trinomial, is basically what we have on top, by something, by one term, that h needs to divide into every single piece. So it cancels out an h here and an h here, and an h here, and an h here. So what we have left is really 2x plus h minus 4. That is the answer to this difference quotient problem. Okay, so we've kind of had a lot of stuff in this section. Go back and watch the different pieces with examples that you need to practice more on, you think, and then go back into ALEKS and practice these objectives. But this is section 2.5.